Welcome back to educator.com. Welcome back to linear algebra. Last lesson we continued to talk about linear transformations. Today we're going to take a brief respite from that, talk about something a little bit more practical, something that you've seen before, but we're just going to discuss lines and planes before we actually launch into a study of the structure of linear mappings when we get into vector spaces next. But so some of this that we do today will be familiar, perhaps some of it will be different, maybe some of the techniques will be a little bit new. In any case, let's just dive right in. So again, we're going to talk about lines and planes. Okay, let's talk about lines in R2. We know that ax plus by plus c is the equation of a line. You're often used to seeing the c on the other side. It doesn't really matter where you put it. Believe it or not, it's actually better to put it this way, to have the 0 over here. That way all of the constants and all of the variables are on one side and the 0 is over on this side, because this idea of homogeneous systems is going to be very, very important for us, because remember we discussed homogeneous systems and the conditions under which a homogeneous system has a solution where the determinant of the particular matrix, the coefficient matrix, is equal to 0 and things like that. So it's often best to write it this way, and it's more consistent when you move on to planes and equations of things called hyperplanes in n-space, which are just the analogs of lines and planes in the spaces that you know, R2 and R3. Okay, well, if I have some point P is xy, and I have, actually this is P1, so x1, y1, and if I have a point P2, which is x2, y2, well, if these 2 points are on that line, then they satisfy the following. You basically just put the x1, y1 in for x and y, so you get ax1 plus by1 plus c equals 0. Actually, I don't need that c1 because c is constant. And I have a times x2 plus b times y2 plus c equals 0. So these 2 points satisfy, if they're on that line, they satisfy this relation, right? Well, let's write all three. Let's write the generic version and these one on top of the other. So we have ax plus by plus c equals 0, ax1 plus by1 plus c equals 0, a x2 plus by2 plus c equals 0. And now take a look at this. This is a system. It has, we have 3 equations. We have 2 unknowns, x and y. We have some coefficients. We have, let me highlight these in red. We have a, we have b, c, a, b, c, a, b, c, and then we have the x, the x1, the x2, we have the y2, the y1, and the y. We can actually write this as a matrix times a vector. So what we're looking for here are the a, the b, and the c. So these x's and y's are actually the things that become the coefficients, and the coefficient in front of the c is the 1. So let me rewrite this in matrix form as, let me actually do it this way, x, y, 1, that's this, this, and the coefficient here is 1, x1, y1, 1, x2, y2, 1, this is our matrix, and then multiplied by the a, the b, and the c. So the a, b, and c are the 3 numbers that we're actually looking for, and that's equal to, well, 0, 0, 0. Again, it's 0 on the right. So this is a homogeneous system. This is a homogeneous system, and this is the matrix representation. So given 2 points and this equation that we know, we can set up this homogeneous system, and now we know how to solve this. As it turns out, so these are numbers, these are actual numbers. These x and y, they stay as variables. That's why they have no subscript. So because this is a 3 by 3, it's an n by n, and it's a homogeneous system, we know that it has a solution, a non-trivial solution, if the determinant of this matrix is equal to 0. That's one of our theorems from some lessons past. So let's go ahead and set up this determinant. Now let me actually write that down specifically. So the determinant of, in this case, let's call the matrix A equal to 0, it implies that there exists a solution. In other words, ABC can be found. They represent actual numbers. Well, so the symbol for determinant is that straight line, x, y, 1, x1, y1, 1, x2, y2, 1. We want the determinant to be equal to 0. So let's expand the determinant and come up with some equation, conditions on x and y, such that this is satisfied. Okay, so let's go ahead and expand. We're going to expand, of course, because x and y are variables. We're going to expand along that row, okay? So I take my, let me actually do this in blue here. So I'm going to knock that out. So what I end up with is x times let me see. You know what? Let's do this a little bit differently. Let's actually stop here. And since we're dealing with x and y, when we actually do some numbers in here, then we'll do the expansion. So again, you're going to expand along the first row, but this is what's going on here. So when you have 2 points, x1, y1, x2, y2, you can set up this matrix, solve for the determinant, and you'll actually get your equation of your particular line, which is the original line that we were looking for. So let's actually do an example. Let's take the point, actually let me move forward one. Let's take the point P1 as -1, 3, and let's take point P2 as 4 and 6. Okay, and now let's set up our determinant as before. We have x, y, and 1. So the variable stays the variable. And of course, we want this determinant to equal 0. We take the first point. It's going to be -1 and 3 and 1. And this stays 1. And the second point is 4 and 6. So we put 4 and 6. And now we can go ahead and expand this and actually see what the equation turns out to be. So again, I'm going to expand along the first row. So when I do that, I end up with x times this determinant, 3 minus 6. Okay, and I move to the next one, which is going to be a minus. So you remember plus, minus, plus, minus, plus, minus. We alternate signs. So it's going to be minus that entry that I'm crossing out times -1 times 1 minus 1 times 4 plus 1 times -1 times 6 is -6 minus 12. And we end up with 3 minus 6 is minus 3x. Here we end up with minus 5 times a minus y. This is going to be plus 5y. And then this is going to be minus 6 minus 12. This is minus 18. And again, this determinant is equal to 0. This is the equation of our line. Now, yes, can you write this as minus 3x plus 5y equals 18? You can. Can you write this as 3x minus 5y equals minus 18? Yes, you can. It's a personal choice. I personally like to see everything in the same form that I did the mathematics. I don't believe in simplification simply for the sake of making something aesthetically more pleasing. As it turns out, the more you see of the mathematics, even though it might look more complicated, more symbolism, it actually is more clear. That means there's more on the table that you see. So again, it's a personal choice. I'll go ahead and leave it like that. Okay, now let's talk about lines in R3. So we just talked about lines in the plane. Now we're going to talk about lines in actual space. Slightly more complicated, but not too bad. Okay, so recall that vectors and points are just different representations of the same thing. Representations of the same thing. Sometimes we think of a point in space as a point, the coordinate x, y, z. Sometimes we think of it as a vector from the origin to that point. So we can write the point, let's say P0, which is some x, y, z. Okay, it's equivalent to, well, two symbols, the vector P0. Okay, now we will let u be a vector in R3. So this is the set symbolism. U is a member of R3. And we will let u, we'll represent it by its component form, point form, u1, u2, u3. So vector form, point form. Okay, the equation of a line in space. Equation of a line in space is, again, we're talking about points in space, so we're talking about vectors. Well, so I'm going to give you the vector representation, and then I'll go ahead and talk about the breakdown. So is some point is a reference point plus some scalar times a vector in a given direction. Okay, t in R, and I'll explain what all of this means in a second. So P0 is a reference point. It is some point on the particular line. I have to pick some point to start off with. U, the vector, is the direction from that reference point, either this way or that way. And again, some of this will make sense when we actually do a problem. Let me draw a picture here of our coordinate system, our right-handed coordinate system. We have x, we have y, we have z. I'm not going to label them, I hope you don't mind. This is that. We move on to red. So I'm going to put point P0 over here. That's my reference point. Now, my vector t, let's just say u, is in that direction. So I have a point P, the line through point P in the direction of u. Well, it's one direction. That's another direction. And that's what's happening. This point P also happens to be a vector, my reference point, my reference vector, and then plus u can be any vector of any length, but t is that scalar that you're multiplying by to make it bigger or smaller. So starting at t, I can go this way, that way. By changing t and having it run through all real numbers, moves in this direction. Or if I multiply it in the negative direction, I can go this way, that way, that way. So this is actually how it's represented. Now, this is a vector representation. Well, as you know, a vector represents just points. So let me see if we can't. Well, actually, I'm going to hold off on the parametric representation for a second, but I'd like you to just sort of see what this is. So the equation for a line is this equation right here. It says that any point can be gotten to by starting at a reference point here and moving in the direction of u, depending on what this is, either forward or backward, to get the entire line. That's what's happening. Okay. So let's see, let's write, let me go back to blue here. Let's write this again. X vector is equal to some p plus t times u. Okay. Well, this can be represented as, well, x1, x2, x3. Again, points and vectors are the same thing. If you want to actually expand it, this is just a shorthand notation. P0, what did we call P0? Let's just say, I don't know, let's call it Z1. Now let's do W1, W2, W3. The symbolism doesn't matter. W1, W2, W3 plus T times U1, U2, U3. So this is actually equivalent to 3 equations. Notice it's the same as x1 is equal to W1 plus T U1, x2 equals W2 plus T times U2, and x3 equals W3 plus T times U3. Okay. Vector form, component form. I broke it up. These are called the parametric equations. The component parametric equations. This is also called a parametric equation. And it's called a parametric equation because you have a parameter. Your parameter is t. That's something that varies, and it expresses a relationship between some point and another point based on some parameter. That's what's changing. You're not actually expressing a direct relationship between the 2 points. You're expressing it using a third parameter, or a parameter in this case, a third entity, if you will. Okay. Okay. So let's do an example. Example will be, let's find parametric equations. So find parametric equations for the line through the point 3. Let me make this a little bit clearer here. 3, 2, -1. I'm not sure if that's much clearer. In the direction of the vector 2, -3, and 4. So we want the line to pass through this point, and we want it to move in the direction of that point, both directions, positive and negative. Well, you can just read it right off. Again, the equation of the line says you just take your reference point and you add some parameter t times the vector u. Well, in component form, it's like this. So we just take x1, w1, tu1. Okay? So we want it to pass through this point. So our x value of the point that we want is equal to 3. That's the point that it passes through in the direction of that vector, plus t times 2. I'll write it this way just to be consistent. You could write 2t. It's not a problem, but I'll just keep it consistent because here I put the t actually before the vector. x2 is equal to 2 minus t times -3. And x3 is equal to -1 plus t times 4. Or if you prefer something a little bit more normal, x equals 3 plus 2t, y equals 2 plus 3t minus minus, you get a plus, and z is equal to -1 plus 4t. These equations, they give you the x, the y, and the z coordinate of all the points that are on this line that pass through this point and are in the direction of this vector. Okay? Okay, let's do another example here. Let's see. Find, let me move on to blue. Find parametric equations. For the line through the point P0, which is 2, 3, negative 5. And P1, which is 3, minus 2, 7. Okay. Well, so we have a point, and we can pick either point as far as our reference is concerned because we're given two of them. We need a direction vector. Well, the direction vector is, well, if you have a point P0 and a point P1, that's usually a pretty good direction vector. So just take this one minus that one. That's how we get a vector in that direction, right? So what we want to take is the direction vector P0, P1, and so I've chosen 1 as my head and 0 as my tail of my, I can do it in either way. I just happen to have made a choice. So that's going to equal to, let's see, 3 minus 2, minus 2, minus 3, 7, minus a minus 5. That's how we get a vector. We just take the arrow, the head, minus the tail. So we end up with 1, minus 5, and 12. So this is my direction vector. And now I can just read it right off. X sub, that's okay, I'll do it here. Once again, x is equal to p sub 0 plus t times my direction vector, which is now that one. So I will say, I will call this x, y, and z. I want parametric equations. P0, 2, 3, negative 5, 2, 3, negative 5. Here's my direction vector, plus 1t minus 5t plus 12t. Through this point and through this point, I have a direction vector. I've chosen one of the points as my reference. I've chosen the 2, 3, negative 5. So these are the parametric equations for a line passing through those 2 points. Okay. And again, I could have chosen the other point. It doesn't really matter as long as there's a point on that line. Okay, let's do something here. Make some room. Let me rewrite. So we have x equals some x sub 0 plus t u1. Y is equal to y sub 0 plus t u2. And z is equal to z sub 0 plus t u3. That's all we've done here. This is just a generalized version. Now t is the same. T is always going to be the same here. 5, 6, negative 6, radical 2, 18, 40. Well, because it's the same, I can solve each of these equations for t. So I end up with the following. T equals x minus x0 over u1. It's equal to y minus y0 over u2 equals z minus z0 over u3. This version of it, when I actually solve for the parameter and express the relationship this way, this is called the symmetric form of the line. So we have the vector representation, which is this. We have the parametric, well, this is the parametric vector representation. This is the parametric component representation. It just breaks this one up so you actually see everything. And then we can rearrange this, and this is called the symmetric form of the line. Again, it's just different ways of representing something for different possible techniques. Certain problems require one form or over another. It makes it easier. Excuse me. So we'll leave you with that. Okay, let's move on to, so we did lines in R2, and then we moved to 3 space. We did lines in R3. Now we're going to move on to planes in R3. Okay. A plane in R3. Is obtained by specifying a point in the plane and a vector perpendicular to it. It'll make sense in a minute when we draw the picture. This vector is called a normal vector. So any vector that's normal to a plane is perpendicular to every point in that plane. That's what normal actually means. Okay, let's draw a picture of this. This is important. So let's draw our right-hand coordinate system. And I'm going to pick 3 points, one on this axis, one on this axis, one on this axis, so that we actually can have a good visual of a plane. So we have a plane passing through these 3 points in the XYZ coordinate system. Now, if I take a point there, and if I have a vector, okay, and let's say I have a, so this is a plane here, and let's say I draw another point there. So I will call this one P0, and I'll just call this one P. Well, the perpendicular, and this is N, that's our normal vector, and this is what's happening. So as it turns out, you can take a point in the plane, and as long as you specify a vector that's actually normal to it, as it turns out, you've defined every single point in that plane, and we'll talk about it in just a minute. So let me represent these as with their components. So the vector n is n1, n2, n3. P0 is, let's call it x0, y0, z0, and point P, we'll just call it x, y, z. So we want a way to represent all the points of that plane. So we're looking for ultimately an equation in x, y, and z, some relationship that exists among these values. Okay, so let's take this vector right here, because we know that 2 points in the plane, they represent a vector if I just take the head of the vector minus the tail. So let me also specify P0, P, that vector from here to P. This is not a P0. Excuse me, that's just a regular P. Well, that equals, well, we take this one minus that one, so x minus x0, y minus y0, and z minus z0. So now I have all of my components. Okay, well, this vector made of the 2 points in the plane is perpendicular to this vector, right? Right, and what do we know about two vectors that are perpendicular to each other? They're orthogonal to each other. Orthogonality means that their dot product is 0. So let's set up that equation and see what happens. So my vector P0P, which is this vector right here, dotted with n, is equal to 0. That's the definition. I'm looking for a normal vector. So now let's go ahead and solve this dot product based on the components. Well, that's equal to this times that plus this times that plus this times that equal to 0. So I get n1 times x minus x0 plus n2 times y minus y0 plus n3 times z minus z0 equals 0. This is my equation for a plane. Now, I can expand this out. I can do n1 times x, minus n times x0. You're going to get numbers. You're going to get an equation in x, y, z precisely because you have variables x, y, and z. Remember, these things with subscripts, they're actual numbers. And these are going to be actual numbers. It's this x, y, and z, the things without subscripts, that are your variables. So now this right here, this is the equation of a plane. Equation of a plane in R3. And again, I just got it by taking 2 points, or 1 point actually, and specifying the vector that's normal to it. Because if it's normal to that 1 point, well, it's going to be normal to every other point in the plane. Okay, let's do an example. Find the equation of the plane passing through 2, 4, 3, and perpendicular to that's fine. Perpendicular to 5, minus 2, and 3. So we want to find the equation of the plane that passes through this point and is perpendicular to this vector. And again, any point in the plane, if one point is perpendicular to that vector, every point in that plane is perpendicular to that vector. That's the whole idea behind choosing a normal vector. Well, let's just multiply it out based on the equation that we just had in the previous slide. We take 5 times x minus 2 plus minus 2 times y minus 4 plus 3 times z minus 3 equal to 0. 5 times x minus 2 minus 2 times y minus 4 plus 3 times z minus 3 is equal to 0. We can stop there. That's fine. This is actually a perfectly valid equation. I like this because I like to see, again, I like to see the dot product, that the multiplication that I'm doing. One component times another plus one component times another. If you want, you can multiply this out. It's not a problem. So if you end up with something like 5x minus 10 minus 2y plus 8 plus 3z minus 9 is equal to 0. So you end up with 5x minus 2y plus 3z plus 1 is equal to 0. This is perfectly valid, and it's the one that you're accustomed to seeing, of course. It's a personal choice. I like this one because I like to see everything that I'm doing. I prefer a longer expression, more complicated expression, as opposed to things being hidden. I see what's going on. I can see the normal vector, the components of the normal vector. I can see my point, 2, 4, 3. I can see them. It's hidden in here. I've multiplied it out. So simplification makes things look prettier, doesn't necessarily simplify the material. Okay. Let's do one final example. Find an equation of the plane passing through the 3 points. So this time, passing through 3 points. Well, there are a couple of ways to do this. Let's do it the way we did for R2. So our 3 points are going to be 2, negative 2, 1, minus 1, 0, 3, and 5, minus 3, and 4. Okay. If it passes through, so we know that the equation of a line, or the equation of a plane, is this ax plus by plus c, ax plus by plus cz plus d equals 0. This is a generic equation for a plane. If for these 3 points to be on this plane, they actually have to satisfy this. So I can just put all of these in here, and then I can, along with that equation, so I could do 1, 2, 3 for the 3 points, plus my original generic equation, I end up with 4 equations and 3 unknowns, just like I did for the first time around. I end up with a 1, 2, 3, 4, 1, 2, 3, 4. I end up with a 4 by 4 linear, 4 by 4 matrix. Well, a 4 by 4 matrix, it has a solution if the determinant of that matrix, because it's homogeneous, they're all equal to 0, is equal to 0. Therefore, I can set up the following. X, Y, Z, 1, that's that coefficient, that coefficient, that coefficient, and that coefficient, the 1. What I'm looking for is A, B, C, and D. Those are my variables. And then I take the point, 2 minus 2, 1, 2 minus 2, 1, 1. I take the other point, minus 1, 0, 3, 1, and 5 minus 3, 4, 5 minus 3, 4, 1. This determinant has to equal 0. And again, I'm going to expand along the first row. It actually doesn't matter where you expand, you're going to get the same answer. So don't feel like you're stuck with the first row. It's just that's the row where the variables happen to be, so I just sort of prefer it. When you do this expansion, and again, it's a little more complicated, but you've done the expansion before, you end up with the following. 8x plus 15y minus 3z plus 17 is equal to 0. In this case, we do end up with this sort of simplified version because we don't necessarily have a normal vector. So there you go. If you're given a point and a vector, you can go ahead and just write it out, take the dot product, and get that very, very simple equation for a plane. Or if you're given the 3 points separately, you can just set up this determinant, set it equal to 0, and solve it that way for the particular equation. Thank you for joining us for Lines and Planes. Thank you for joining us at educator.com and Linear Algebra. We'll see you next time.